Welcome friends, let's do a series expansion for 1 over x. Let's do this about x equals positive 2. So I'm going to use the geometric series approach. That means the following. I can begin by writing 1 over x is equal to 1 over 2 plus x minus 2. This is allowed because 2 minus 2 is 0. You're not changing anything. So it's more like 1 over 2, and then if you want it to be a bit more careful, within parentheses x minus 2. Again, 2 plus 2, 2 minus 2 is 0. Then I factor 1/2 out this way, separate it away. So that means what we have left over is 1 plus x minus 2 divided by 2. This is allowed because if I bring the 2 across each term there, it's going to be 2 plus the 2's will cancel, giving back x minus 2. And lastly, for the geometric series where the plus is meaning a minus, I got to write 1/2 and then 1 over 1 minus, and let's say within bracket we'll do negative x minus 2 divided by 2 this way. Now this looks appropriate. Let's just confirm something kind of important, that these are really the same things, because when you look at 1 over x, when you look at this form, they look so different, obviously. So the question is, are they really different though? So a way to answer this would be to try to graph it. You see now one second. Okay, let me try that again. Okay, so let's graph this. So let me graph 1 over x. Okay, let's zoom in on what's interesting here, which is like the region close to the origin 0, 0. Okay, and now let's graph also this seemingly very different looking expression. 1/2 times 1 minus the negative x over 2 divided by 2, right? They look so different, obviously, but look what happens. When you graph them, they're identical. That means that's it, they're identical. They're interchangeable. They represent the same thing. Otherwise, I would have two different looking graphs. Okay, anyway, so with that in place, now you can use the geometric series. We can write 1/2 that we separated away, and the other part can be the summation as n goes from 0 to positive infinity. So from 0 to positive infinity, not 1. And there, that would be the negative x minus 2, yeah, divided by 2, and this whole thing raised to the n this way. Now you can distribute the n and bring the 1/2 across. So it's going to be the summation as n goes from 0 to positive infinity. And then it's going to be, well, okay, so there's also a negative. You can send the n over to the negative. So you're going to have, in other words, a -1 for that reason to the n. This 2 in the bottom multiplied by that 2 after you distribute the n to it would give you the following. So let me be careful. You would have, in other words, x minus 2 to the n. And then at first you would have 2 times 2 to the n as a kind of intermediate step. That means lastly you would have the summation as n goes from 0 to positive infinity. -1 raised to the n, and then x minus 2 raised to the n divided by 2 to the n plus 1. Let's write out a few terms just to convince ourselves this actually matches our function of x equals positive 2. So what I'll do, hold on. Yeah, okay, I'll get to that in a second. I'll graph it also. So when n has the value 0, you plug it in. That's all, plug it in. So when n is 0, -1 to the 0 is 1. When n is 0, x minus 2 to the 0 is 1. When n is 0, well, 0 plus 1 is 1, 2 to the first is 2. So you have this left over. Next one. When n is 1, that would become a -1 times x minus 2. When n is 1, so it becomes x over 2, then it's 1 plus 1, and then 2 to the second, like this, you see? Let's do one more. So when n is 0, 1, 2, so when n is 2, you have -1 squared, which is a positive 1. Then you'd have x minus 2 to the second. And the bottom would be 2 plus 1, which is 3, so 2 cubed. And then minus ... ellipses to indicate the pattern continues that way. So let's do this. Let's graph some stuff now. So I would have a half essentially, right? Minus x minus 2 divided by 4, and then plus x minus 2 cubed divided by 8. So I'm arbitrarily, because I feel like it, I'm taking the first 3 terms. I could, write out a few more, but this gets the idea across. And notice that the red graph and the green graph agree at x equals positive 2. So really, let's just kind of study that a little bit more closely. Okay, so what's interesting here? The interesting region is this one. You see how they agree very closely? Well, they're identical at x equals positive 2 because that's the way the stuff is designed, right? If you plug a 2 in here, then 2 minus 2 is 0, 2 minus 2 is 0. You see all the terms containing x minus 2, all those terms vanish, and only the constant 1/2 is left over. All right, but as you can see, there's also a gap that begins to form to indicate the error. You can do the error here as follows. So error is pretty much, you can define it as follows. So it's the function, so 1 over x, minus the approximation, let's say using the first three terms. So the minus the 1/2, minus the x minus 2 over the 4, and then plus the x minus 2 squared over the 8, like this. So this is just the error. It's just a little vertical separation between the graph of the function and then also the approximation. So let me delete. I can even do it in here. Why not? So let me see. Maybe I can punch the whole thing in here. Hold on. See? So I'm taking the error and absolute value, the function, minus the three terms from the approximation. Notice the three terms from the approximation get it enclosed within parentheses, so everything works out. And if I look at the error, it's the blue graph. So let's just do this. It's a bit instructive to look at this. Okay, if you look at it very carefully, and then I'm going to just maybe, okay, get the right effect to show up here. So as you can see, at x equals positive 2, the blue graph has a value of 0 in terms of its y-coordinate because it's the error function. That means that these graphs right here match perfectly at x equals 2. As you tend away from 2 towards the left, the error increases. As you tend away from 2 towards the right, the error also increases, as it should. Lastly, we should look at the interval of convergence. So take this part right here, this part that you plug in, and now like this, you see x minus 2 over 2, and this has to be less than 1 to get from the geometric series, right? Okay, so the negative gets gotten rid of by the absolute value, so that leaves just x minus 2 divided by 2 is less than 1. But then you can multiply across by 2, clear the 2 on the bottom, 1 times 2 is 2 on the right, so it's absolute value of x minus 2 less than 2. All right, and then drop the bars, move the 2 left, so negative 2 is less than x minus 2 less than 2. Standard way of solving absolute value inequalities. Then add 2 to every term, negative 2 plus 2 is 0. Negative 2 plus 2 is 0, leaving x in the middle, and then 2 plus 2 is 4. So this is our interval of convergence. In other words, what it's telling you, what does it actually mean, interval of convergence? Notice that, for example, like x equals 1, right, like belongs to this. Okay, it's an element of this interval from 0 to 4. Okay, x equals 1 is an element of the interval from 0 to 4, right here. So what it's telling you is if you took enough terms, okay, here, you can make the graph an approximation match at x equals positive 1, you see? On the other hand, let me stress, if you took x equals 5, like this, right, that's not an element, right? That's definitely not an element of this interval from 0 to 4, correct? So you couldn't make the match, that's all. I'll leave it here. So if it's been helpful, leave a like. Thank you.